last lecture, we were talking about basics of linear algebra, and we were talking about matrix multiplication, different interpretation of matrix multiplications. Today, we are going to talk about different kind of transformations which can be performed using those matrix multiplication operations. Basically, we will try to cover three types of transformations, starting off with scaling. Then we'll talk about rotation, and then how we can perform translation operation in vectors or in matrices. Okay, so matrix multiplication, we studied this last time. We know that there should be some compatibility between two matrices, and this matrix multiplication can actually be used to perform scaling of vectors. For example, let's say we have a vector x, and we want to scale the values of this vector and transform it to, let's say, x prime. And so this operation can be easily, or this transformation can be easily done using a matrix multiplication. In this case, the matrix is A. And if you look at this equation here, the matrix on the left, that's the transformation matrix, which can be used for scaling. And this is the original vector we have x. So the values are x and y. And this matrix over here, you can see that we only have diagonal elements, and these are Sx and Sy, the rest are 0. And if you perform this matrix multiplication operation, these are the numbers you will get. And here you can see that the x value is being multiplied by Sx, and y value is being multiplied by Sy, which is kind of a scaling operation which we are performing independent on these two dimensions. All right. So another way to interpret this, it could be like last time we saw, if we perform multiplication of two different matrices, it can be interpreted as a linear combination of either columns or rows. In this case, I think linear combination of column is more important. So here you can see that what we are in fact doing is we have two columns in this matrix, and we are just performing a linear combination of these columns. And the weights which are being used are the original vector values x and y. Okay, so the first column vector is actually being scaled using x, which is giving you Sx, and the second is actually being scaled with the value of y, which is giving you Sxy, right? So that was scaling. Let's move on to rotation. Rotation, I think this operation is pretty interesting, and it's a little bit involved, so bear with me. I will try to explain it very slowly. The idea is, let's say we have a vector shown here like x, y in this coordinate system. And what we want to do is we want to transform this vector with an angle theta. So the resultant vector is going to be x prime, y prime, and the angle between these two vectors is going to be theta. Okay, so we want to perform that operation. And let's try to understand how this can be done using matrix multiplication. So first of all, we will need like a rotation matrix, which will be used for this operation. And first, let me show you that matrix like upfront. So that matrix is, if you have to rotate any vector with an angle theta, then this is the matrix which will be used. And the values here are like cos theta, negative sine theta, and cos theta. We'll briefly talk about like how to derive these values and how this operation is actually performing rotation. But this is the matrix which is called rotation matrix. And if this is a vector xy and you multiply with this matrix, you are going to get a vector which is x prime, y prime, and the operation is going to be rotation of this vector to get this x prime, y prime, which is shown over on this plot here. All right. So if you perform this operation, then I think that's basic matrix multiplication. You will get these values, which will give you x prime and y prime. Okay, so let's quickly go over like how this operation leads to a rotation of vector. Now, before going to rotating a vector, let's talk about, can we rotate the axis of this coordinate system? Okay, so the coordinate system we have here is, this is like x-axis and this is y-axis shown in the blue. And what we want to do here is we want to rotate like this axis with an angle of theta, and the resultant axis is then going to be the x prime and y prime in that direction. All right. So initially, let's say the vector we had is v. So this point over here. All right, so that's the vector v. It will start from this origin. And it's represented by x and y, which means that the projection of this vector on x-axis, that distance is actually x, right? So this x is also the distance from the origin. And y is the projection of this vector on the y-axis, again, which is also distance of this point over y from origin, right? So that x and y represents the original vector v. Now, once we transform the x's, then what's going to happen is the axis is now not this blue one, this red one. And the question is how we represent this point in this new rotated axis. Okay. So what we'll have to do is, first we need to find out what is the component of this vector v in this new axis, which is x prime, and what's the component along y prime. Okay. So the x component in new x-axis, it will be like starting from this location all the way up to here, right? And y component is going to be starting from this all the way up to this point. Now, if you remember, like a vector dot product, which we discussed last time, so this is like the projection. And if you have two vectors a and b, and let's say b is your unit vector, then a cos theta actually gives you projection of a on b, right? And similarly, in this case, we know that this x-axis, which is shown using blue, is a unit vector. And if we take projection of the original vector v on that, that's going to give you x. Similarly, projection of that on y-axis is going to give you y. Okay, so remember that a cos theta is like projection on this x-axis, and a sine theta will be projection on this y-axis, perpendicular drop from here. So the first thing we'll have to do is we'll have to find out what is like the new axis and new y-axis after this rotation, because we need the axis to find the projections first, right? So let's say this x prime and y prime is like the new axis we have. And again, as I said, x prime is going to be the v vector, right? And you'll have to compute the dot product with the new x-axis of v. That is going to give you x prime. And again, y prime is going to be the dot product of v, again with the new y-axis. Okay. So if you have to rotate like with angle theta, if you think about this, if this red one is your new axis, and axis you always determine with like unit vector. Okay, so you start from this location, and if you move like, let's say, unit length, which is like one unit, so that is going to be your x prime axis in this direction. And if you take a point, let's say 1 unit in this direction, so corresponding to the original blue axis, x and y, this point is going to be, if you think about this, so this, if you drop a perpendicular on this x1, this is going to be x cos theta, right? And this is going to be x sine theta. So that unit vector in this direction, the coordinate value will be x sine theta, sorry, x cos theta in x and x sine theta in y. But x we know is 1 because it's a unit vector. So you can represent that as cos theta and sine theta. So this is kind of your new axis in terms of the older axis. Similarly, you can find the y-axis. Of course, for that, you'll have to actually project this y into this one. So again, you will take unit vector in y direction and project on this, you will take a unit vector in this red direction and going to project that on y. And in this case, you can see like cos theta will drop here. So this is again your y direction. So the second value is cos theta. And if you take the sine, which is the perpendicular drop over here, that's going to be your x direction, but it's in the opposite direction, right? Towards the left. So that's going to be a negative sine theta. So which means that the unit vectors in x prime and y prime coordinate axis are going to be this. And that's exactly what you need to compute this dot product. You have the vector v, you just needed the new x-axis and new y-axis. So let's complete that. So your new axis now you have, you know how to compute x prime and y prime. you can just formulate like a matrix formulation or matrix multiplication formulation for this. And this is going to be the matrix. Okay, so you can just put these as rows in this matrix. So that's the first one corresponding to x-axis. That's corresponding to y-axis. And if you do the multiplication, it's going to give you x prime and y prime. So this was about just rotating the axis, not the vector itself. But now if you think about this, if you are rotating your axis, let's say with the angle theta, then that's kind of you're rotating your points towards right with angle negative theta. It's kind of equivalent. So now we know how to rotate the axis. To rotate the vector, you can just negate the angular value and use the same matrix. All right, so if you have to rotate the vector, what you can do is just invert like the angle. You can replace the original matrix we computed with negative theta and put in this equation. That's what you will get. Cos theta will remain cos theta. Sin theta, the angle will be like reverse. Okay, so that's how you obtain your rotation matrix if you want to rotate your vector with angle theta. All right, so that was rotation. The third and final transformation we are going to talk about is translation. Now, before we talk about that, let's try to combine what we have covered so far. We have covered scaling and we have covered rotation. And we have seen that like just 2 cross 2 matrix is sufficient. And given any matrix, which is 2 cross 2, if we multiply that with a vector, then this operation is going to perform rotation as well as scaling. All right. But again, it depends on the values, like how much it will be rotated or how much it will be scaled. But this kind of matrix is sufficient for scaling, rotation, and it also performs skew transformations. But still, we are not seeing any shifting. Okay, we are not seeing shifting because if you see like the final values of the coordinate, it's still like the linear combination of your original values. So it's again relative to whatever you had earlier. So you're not actually performing any shifting. Shifting will be something when it's independent of the original values. Okay, so let's see how we can perform shifting. There is a very simple trick. What we do is we expand the matrix. Instead of 2 cross 2, we create a 3 cross 3 matrix and add like this row and this column here with a 1 here. And we increase like the dimensionality of a vector, just add a dummy 1. And if you perform this operation, matrix multiplication, you will see like you are getting this matrix over here. And if you ignore this 1 over here, you still get the same transformations, which you were getting earlier using a matrix, which was 2 cross 2, having value A, B, C, and D. All right, so nothing has changed. It's just like extra amount of computations, but still you are able to perform the same set of operations. Okay. Now let's see how we can use this to perform shifting. Now what we can do is in the last column over here, we can add these values, let's say C and F. And if we perform this matrix multiplication, this will be the resultant vector values. And you can see here that these values are actually getting added to these vectors. C is like coming from the first one, F is being coming from the second one. All right. So in this case, we are actually shifting this vector by amount C in x-axis and by F in the second, which is y-axis. Yeah, so then, all right, and you can again just ignore this last row over here. This is the final result. And again, if you think about like the way we described matrix multiplication in the last lecture, when we try to multiply two matrices, the resultant matrix, the first column is going to be linear combination of these columns. And that is exactly what is happening here. So if you look at this, the first column has a weight of x, right? A and D are being multiplied by x over here. And the second column is again has a weight of y. You can see like y being multiplied by B and E over here. And the third one, that's the weight for the last column. In this case, it's 1, which is making us like spatial and independent of x and y values. Okay, so that's like another interpretation you can think of. And this allows you to perform shifting. So this matrix over here, this is called homogeneous coordinates, and or you can say homogeneous system. And the system allows you to perform all these transformation operations on your vector, or you can say like a matrix as well. If you put all of this together, then you can have like a single matrix, a 3 cross 3 matrix, which is called like a homogeneous matrix. And you can just multiply all these three matrices to get a single matrix, or you can have like them as separate. We have shown in this equation over here. So you start with like the translation, then this is the rotation, and this is the scaling. And of course, you can't like switch the order here. That will change the meaning of your operations. All right. So this is like everything on the same matrix.